You have, well, you do have a home with you on Wednesday, on Monday, right here. Yeah. Okay, I guess I'll sign it. Okay, this will be, you see the justification of the name on this one, in the next one. Okay, so what does it mean finding the first order plus time delay transfer function? It means finding the three parameters, k, tau, and d. So what's the very first thing I should start with? K. K. K is what? So, K is delta y over delta u. What's my delta y? Change by 5, right? Don't write that down there. What's my delta u? It's 2.5 GPM. Units don't matter.
What's a GPM?
Gallons per minute.
What?
Gallons per minute.
Oh.
Don't write that down, does it?
Well, it might come up.
If I had done this in the exam, I probably would have gotten no credit at all in the program. Why? Robert?
The temperature decrease, so it should be negative.
Yes. And the result is, as Robert said, the temperature should be negative. That's the one algebra error. You go back your exam, some of you had arithmetic algebra errors. It was clear to me that was simply an arithmetic algebra error. I put a -0 in your exam. I didn't take anything off. If you mess up that sign, I may give you 0 partial credit.
The abomination.
Always make the mental check. If the input and measurement moving in the same direction, if they are, it should be positive. If they move in opposite direction, it should be negative. So, you calculate something, stop, check. What do I have here? Flow rate of coolant and temperature measurement. If I increase flow rate of coolant, what happens to temperature measurement? Goes down. Opposite direction should be minus. And the mistake is that what Robert said, let me write some specific information here. Delta you should take consistently, so that would be y nu minus y beginning. U nu minus u beginning. So the y nu is what? 47. The y beginning, 52. The change in u, I'm saying u was increased by 2.5, so that's plus 2.5. So it's -2. So that's the first thing that we do. Okay? Next, I need to draw a slope line. So I need to get my very accurate ruler. And with my very accurate ruler, I play with the ruler. You want to find the section where it's a straight line. And draw a tangent line on that straight line. And for the do not use method, you need to draw it.
You start from the top.
Hmm?
Can you do that one more? Like, do you move the ruler from the top or the bottom of the curve? I don't know.
You have a transparent ruler. Okay, here, let me do some on the side. Let's say it looks like that.
Yeah.
Find the straight line portion. This is where you need to draw it. Here is a bad one. This loses points. That's not tangent. Here's another bad one. What's wrong with that one? Why is this wrong? This is right. A tangent line will have the experimental data on either side of the tangent point. You see, data here are below and above. If I draw this, notice I have data on the same side. That's not the tangent point. The correct point should have your data on either side. Where's the correct point here? It's here. Draw that straight line, and you see orange on either side. Clear? And it must be coincide with the data in more than one point. I've seen students draw tangent lines that look like that. Terrible.
Can you explain?
Okay? And up or down. So we draw the tangent line, the slope line. Now I need to find now where is the corner. So take with the original steady state, and I'm reading here where is the corner. I'm reading this time. So here's 12, 12, 12, 17 looks about 12, 13. So right here is T corner. Remember, T corner is with the original steady state. Don't get the two mixed up. T do not use with the new steady state. Corner with the original. So I find that T corner is 12, 12. 12, 13. Yes?
On this, again, how did you know it's on 12, 13?
Well, okay. I'm reading here that I put here lines where it's 12, 12, so it was 12, 12 here. So that was 12, 12 here. That's here's 12, 17. Okay, 12 was 7, 12, 17. It's a little bit past the midpoint. 12, 13.
So where the lines start to go down?
No, where the line intersects the original steady state. You have the tangent line of that. Don't mind if I kill white chalk, but I don't want to kill a good color chalk, the one you guys can read. Yeah, I'll smooth it. Yeah. With that smoothing, that tangent line will not. So you draw, where was the straight line part? You draw the tangent line, and where that tangent line intersects the original steady state, that time is T corner. So read that time of your chart. So I'm reading here, this is 12 was 7, this is 12, 12 here, 12, 13. This is 12, 17. Okay? So I'm reading T corner equals 12, 13. So the delay is going to be T corner minus T naught. In other words, 12, 13. What is T naught? 12 over 2. Right? So 11. So that's my delay. It's going to be 11 minutes. Then, for the next one, I find T do not use. Draw the intersection with the new steady state. This here is going to be T do not use. That looks like it's maybe 12, 15 or 16, what do you say? Let's say 12, 15. So, T do not use is 12, 15. Andrea?
I still don't understand how you got T corner.
Was that given, or would we have to find?
No, I get it from that. Okay. Let's do it again. I also want you to understand that, so let's do it again. And I'm not going to move on until Andrea tells me I got it. I have the experimental curve. Oh. Okay, Andrea? I find the experimental curve, the straight line portion, where I draw the straight line. I will have data on either side of it. So you can see here's the straight line part. So I will draw it like that. Okay? That's a good slope line. Where did I start? Here. Here's my beginning steady state. Draw the beginning steady state line. When the beginning steady state intersects the slope line, this time here is T corner.
How do you know this slope is right there and not like lower?
Where would you put it? If I put it here, if I try to put it here, notice the origin both on the same side. There's only one point at the inflection point where you have the data on either side of it.
I have a question. I seen it like done before. Like, do you start with the ruler at the top of the graph or at the bottom of the graph? Just move it until it just hits one point.
Yeah, that's why I'm saying a transparent, a clear ruler would be better. It's easier to see it.
So wait, the top? Is that what you're saying?
Well, yeah, you don't need to do that, but if you do that, yes, you can see when you start having. Okay, one suggests
you see what I'm saying?
Yeah, once it is there, take the ruler here and start going this way, and see when the data starts being on both sides.
Yeah.
I think that's not a bad suggestion. I think that's a good suggestion.
So do you start
So
from?
with a clear ruler, you can do that. If you don't have a clear ruler, you have to do it like I'm doing. Okay? Anyway, you understand how we draw the slope line? This is the p-coordinate. Then I also take the intersection with the new steady state. So here's my new steady state, where my data now is going to end up. And this time here is going to be the t. Better? Let's do another. Suppose I'm going up, because this applies going up or down.
Professor, so
Yes.
is it point 11 or it's 11 here in the answer?
11 is the answer. 12, 13 minus 12, what? This is 11. The difference between the two times. So,
Should be point, is it
12, t coordinate was 12, 13. T naught was 1202. The time the step change happened, which I'm telling you happened at 1202. T naught is the time the step change happened.
Yeah, so you subtract them, right?
I subtract T naught from T coordinate.
So you get
You just kind of
point 11.
It's 11 minutes.
It should be, the answer should be point 11. Let's see.
So 11 minutes. This is time. 12, 13 p.m. 12, 17 p.m. I gave you the typical time you would have, because normally you would record the time 42. I give you a more realistic time recording. Okay, so now let's continue. Suppose I had this curve. I wish I had an aspirant ruler, then I would use one suggestion. But you can see here, hopefully you can see that the straight line part that would have data on either side is, yeah, very well. Would be this. In this case, where is the coordinate? With the beginning steady state, right? So t coordinate is here. Don't go always at t coordinate is the high or the low. It's t coordinate wherever it intersects the beginning steady state. Where is t do not use? New steady state here. Here is t do not use. Okay? So, for our example, t do not use, I read this time was about 12:15. Here's 12:17. It's probably 2 minutes away from 12:17. Okay? So, tau is what? T do not use minus t coordinate. Right? We saw that here, that t do not use is t naught plus d plus tau. T naught plus d is what is t coordinate. So tau is t do not use minus t. So in this case, what is tau? So it's 12:15 minus 12:13. 2 minutes. So what is my answer? My answer is that GU equals minus 2 for K over tau is 2, S plus 1, delay is 11, e to the minus 11. Clear? So I taught you the do not use method because you see that in every textbook. And also it shares a lot of features with the method I like to use. One of the two methods I like using. It's 12:20, so I'm going to give you a 15-minute break. And we'll continue at 12:35 and we'll talk about the next method, which I have named the slope line method. It's one of the two without computer, without Excel. 4 methods, Felix. 3 are without Excel. The 5 is with Excel.
Hey, can I move you?
So if all the books only show this one method, why do they prefer this method over the other method?
I honestly don't know. I think someone put it up there and they copied that, everyone, and they never sat down and thought. Now the Smith Code book has all 3. Doesn't criticize it, doesn't